Hi everybody. The main goal of this video is to talk about how you think about the geometry of complex multiplication. So in other words, when I multiply by a complex number, how do you figure out geometrically where the result is? So before we do stuff with complex numbers, let's talk about the geometric meaning of just like regular old real numbers. So if I've got a value x here, if I multiply x by 2, you could think about that as stretching it. So if that's the length to x, and I do that same length again, it seems like it should end up about there. You can think about that as one of these transformations. So we know how to scale things, shift things, reflect things. So it seems like that's scaling or dilating. If I add 1 to x to end up here, that seems like that's translating, because I'm like shifting it over. If I multiply x by -1, this x kind of bounces over to this side, and that seems like it should be reflecting. If I multiply by -2, it reflects over into the negative area, and then I stretch it after that. So here's where -2x would be approximately. So multiply by -2 actually does two things. It reflects and dilates or scales. So all of this is to say that you can imagine multiplication and addition as doing things geometrically on the number line. When I multiply, I stretch the number. When I add, I shift the number. If I multiply by a negative, I reflect the number. Okay, so with those ideas in our mind, let's ask what happens when we multiply by I. So we're going to imagine I and I squared and I cubed and I to the fourth and I to the fifth and I to the sixth. And we're going to ask each time we multiply by I, what happens? So let's draw the complex plane. I didn't mention this in the last video, but we call this the real axis, and you often abbreviate it RE. This is the imaginary axis, which you often abbreviate IM. So let's make that one -1, -I, I. Okay, so if I'm at 1 right here, and then I multiply this number by I end up here. So right away you could ask, is there a transformation geometrically that takes me from here to here? And you could just think about that in your mind. Okay, so let's say I'm at I and I multiply by I again. That gives me I squared. And we knew in the last video that I squared is the same as -1. Because if I equals root -1 and I square both sides, if I square root -1, that gives me -1. So that's why I squared is -1. So that's the point I. This is the point I squared right here. So again, think. I had a number, I multiplied by I, it ended up here. Now I have this number, and I multiply by I, and it ended up here. Okay, what happens when I multiply this by I? That gives me I cubed. Well, I cubed is just like I squared times I. We know I squared is -1. So -1 times I is just -I, which is down here. So this is I cubed. So when I had this number and I multiplied by I, it ended up here. Let's keep going. Let's multiply I cubed by another I. That's I to the fourth. You could think about that this way. -1 times -1 gives us just +1. So this point right here is 1, but it's also I to the fourth. So I think maybe we're ready to give this an interpretation. Each time we multiply by I, it seems as if what's actually happened is we've rotated the number by 90 degrees. I'm not proving anything. We're just running some tests and making some observations. We're making a conjecture, let's say. But it looks like multiplying by I seems to rotate the number by 90 degrees. All right. So, that by itself is kind of interesting, and you might stop to ask yourself, like, what should I to the 100 be? Indeed, stop to ask yourself, what should I to the 100 be? Decide right now. You could think about it this way. Every time I multiply by I 4 times, I end up back at 1. 100 is divisible by 4, so it should just be 1. If we wanted to be like a little bit more careful about it, we could say I to the 100 is the same thing as I to the 4, and then that to the 25th. I to the 4 is the same thing as 1. 1 to the 25th is just 1. So this kind of thinking, imagining multiplying and you sort of like are rotating around the complex plane, this is a very common way of thinking. Okay, so let's test it. So if it's really true that multiplying by I rotates the number by 90 degrees, what happens if we have this complex number? Let's call it A. What happens if we multiply A by I? First, let's decide where is A on the complex plane. So here's I, here's negative I. So you might recognize this as a point on the unit circle. The unit circle is just a radius 1 circle, so, there's nothing stopping us from drawing a circle on the complex plane whose radius is 1. And this point would be about here. So we would have gone a distance, so this distance would be negative root 2 over 2, or rather we're going a distance of root 2 over 2 in the negative direction. Here, the root 2 over 2i means that we're going up the I axis, the imaginary axis, by another root 2 over 2. So there's the point A. Okay, where would we expect A to end up if we rotated it by 90 degrees? Seems like we'd expect it to end up here. The question is, does it? So let's test it out. Here, I'm going to put the I in front, and then I'm going to actually distribute. Okay, so if I distribute the in, I times negative root 2 over 2 gives us negative root 2 over 2i. When I multiply in here, I get root 2 over 2i squared. Okay, but remember, I squared is the same thing as negative 1. So if I replace that with negative 1, now I've got root 2 over 2i minus root 2 over 2. Usually, when you're writing down a complex number in rectangular form, the real part is what you write first, and the imaginary part you write second. So I'm actually going to swap the order here. So negative root 2 over 2 minus root 2 over 2i. Notice that that is exactly where this is. It's negative root 2 over 2, and then I went down the imaginary axis to negative root 2 over 2i. So again, we haven't proven anything, but we made a conjecture that multiplying by I seems like it's rotating by 90 degrees, and we we tested our conjecture with another number that's not I, and it really did seem to take that number and rotate it as well. Okay, let's try one more set of things. Let's imagine complex number A is 1 plus I. Let's go ahead and make the complex plane again. Here's I, here's 2I. So here is the location of A. Go ahead and multiply out. What should A squared be? What should A cubed be? What should A to the 4th be? And then plot them all here. And we'll ask, what does multiplying by this number do? Multiplying by I rotated by 90 degrees. What does that one do? Okay, pause the video and multiply out. Okay, I'm going to multiply out right now, right here. So this is 1 plus I times 1 plus I. So that's going to give us 1 plus 2I plus I squared. I squared is just negative 1. So here I get 2I. So that's where 2I lives. So that's A squared. Okay, let's take that and multiply it by 1 plus I again. So here, when I distribute this in, I get 2I. And then here I get 2I squared. But remember, I squared is negative 1. So that's negative 2 is what the 2I squared was. And then 2I came from here. So that's A cubed. Let's write where that is. So that's negative 2, and then plus 2I is up here. So this is A cubed. Let's take that now and multiply it by another I plus 1. negative 2 plus 2i. All right, so 1 times negative 2 is negative 2. Here I've got 2i. Here I've got negative 2i there. And then plus 2i squared. Okay, the 2i and negative 2i are undoing each other. This has become negative 1. So if I multiply the negative 1 times 2, that gives me negative 2 minus 2, which is negative 4. Interesting. So here is where a to the fourth is. Okay, so if you look at this pattern, a lot of students were starting to draw a kind of spiral, and that's not wrong. But we want to think about, is there a particular geometric transformation that gets from each number to the next one? So when we multiplied by I, we rotated by 90 degrees. When I multiply a by itself, it ends up here. When I multiply this by a, it ends up here. This times a ends up here. So a lot of students said, oh, look, it does seem to be still rotating. It looks like every single time it's rotating by 45 degrees. So it seems like multiplying by a or like multiplying by 1 plus I, again, we're not proving it, but seems to rotate a number by pi over 4, or 45 degrees. But it's not just rotating, because if it was just rotating, we would expect it to sort of like stay here, like in a kind of a circle area. So it's not only rotating, it is also dilating. Not only did we rotate it by 45 degrees, but we stretched the distance. So how far did we stretch the distance? It might look like we doubled the distance, because this feels like it's distance 1, even though it's not. And then this distance is clearly 2. But remember, this distance isn't 1. This distance is actually root 2. And the way you know is because this is 1 and that's 1. So by the Pythagorean theorem, that's root 2. So if that diagonal is root 2 and this vertical is distance 2, what do you have to multiply to get from root 2 up to 2? If I multiply root 2 by itself, that's what gives me 2. And then if I multiply that length of 2 by another root 2, that gives me 2 root 2, which is exactly how far this is. If I multiply 2 root 2 times another root 2, that gives me 4, which is exactly how long that is. So we're not only rotating by pi over 4, we're dilating the distance by root 2. Okay, here's something I want to point out. A is 1 plus I. Notice that the angle to A is pi over 4, and let's see if I can fix this. Haha. And the magnitude of A, like the distance to A, is root 2. So multiplying by A rotated by pi over 4, but that's the same thing as A's angle. It also dilated by a distance of root 2, but that's also A's distance. So this suggests the idea that maybe multiplying by a complex number rotates by whatever that number's angle is, and dilates by whatever that number's distance is. And that's exactly the big idea that we're going to agree upon without proof for now. We're going to come back to the proof later. So the big idea is, if z is a complex number with a particular angle and a particular magnitude, multiplying by z is going to rotate the other number by z's angle, and it's going to scale the other number's magnitude by z's magnitude. So if you want to draw a little picture here, so you can draw your own picture if you want, but let's imagine a complex number a, and we're going to leave it kind of abstract right now. But there's a particular angle that points at A, and let's say its distance is 2. If I take B and I multiply it by A, what's the resulting number? Well, the way to figure it out is to take B and let's rotate it by that same angle. So I'm going to rotate B in this direction by A's angle. So now I know it's kind of in this direction somewhere. And then I'm going to take B's distance and I'm going to stretch it by a factor of 2 because that's A's distance. So if B was a distance of 1, now this point over here is a distance of 2. Let's not label it question mark. Let's label it, I don't know, C. So here we have it, C. So that's just a little illustration. You can use a different illustration if it works better for you. But the idea is when you multiply B by A, it'll rotate by A's angle. It'll stretch by A's distance. A different way, and maybe a more common way of expressing the same idea, is if A and B are two complex numbers and you multiply them, the angle that takes you to C over here is just B's angle plus A's angle. So angles add is the idea. When you multiply two numbers, their angles add to give you the angle of the result. What's the distance to the result? Well, you take the two distances of what you're multiplying and you multiply them. So angles add, distances multiply. And those multiplied distances give you the distance to your result. Some students find it easier to think about this way. Some people find it easier to think about this way. They're both great to think about. This is what you'd more often see in textbooks. But this feels like kind of like a more active way of thinking about it. You're thinking about the action of doing the multiplication and what effect does it have on the other one. Okay, come back in the next video to see how these ideas play out in some interesting contexts.